Hello everyone. Today I will give a presentation on our paper, Enabling Efficient SIMD Acceleration for Virtual Radio Access Network. First, I will introduce the motivation and background of the work. Next, I will go through the architectural implications of the VRAN system. And in the third part, I will illustrate our observed VRAN efficiency and our optimization according to it. Finally, I will demonstrate the evaluations of the VRAN system after the optimization. Now, the new area network enables many new applications which can be hardly done by the former network. The reason why new area network can support these new applications is that the new network has new features compared to the former network. In this paper, we focus on the NFV on the video access network, which we call VRAN. NFV utilizes commercial off-the-shelf servers to realize the network functions which are previously enabled by dedicated hardware. For this part, I will introduce a typical VRAN architecture. The figure shows an uplink path and the key network functions in the InnoB and core network. A data flow is shown in the figure. We choose the OpenAI interface as our VRAN framework because OAI is the most complete open source VRAN platform. The version we use for the InnoB is 2018 W25, and the version we use for the core network is version developed. For this part, I will introduce typical Intel processor architecture and give a brief introduction on how we illustrate the architectural performance. The figure shows typical Intel processor architecture. Considering architectural implications, we utilize 5 typical metrics that illustrate the architectural performance. They are IPC, retiring, front-end bound, bad speculation, and back-end bound. IPC is a matrix indicating the average number of instructions executed for each clock cycle, which is used to measure instruction level parallelism. IPC relates to retiring, front-end bound, back speculation, and back-end bound. Retiring reflects the issued macro operations eventually get retired, while the other 3 metrics means the issued macro operations get stored. Front-end bound denotes that instruction fetch store will prevent core from making forward process due to lack of instructions. The front-end bound happens at the front portion of the processor. Back-end bad speculation reflects loss wasted due to incorrect speculations. The bad speculation happens at the speculation portion of the processor. Back-end bound illustrates that no macro operations are being delivered at the issued pipeline due to the lack of required resources in the backend. The backend bound happens at the back portion of the processor. We first characterize the IPC and CPU utilization for the modules inside the VRAN system. From the figure, we can observe that for both uplink and downlink cases, the IPCs for downlink control information, rate matching, and scrambling are near to the ideal value of 4 for modern Intel processor. All these modules are not CPU consuming. However, the IPC for the most CPU consuming module, tuber decoding, is only around 2.1, which suggests central headroom for optimization. In order to find out the root cause for the poor IPC, we explore the macro-architectural matrix related to IPC. As demonstrated in the macro-architectural profile, the results reveal that across all the modules, the front-end bound and bad speculation overheads are negligible. The main store of the VRAN applications are concentrated on the backend bound, which means the optimization for backend bound is necessary for VRAN applications. Backend bound can be divided to memory bound and core bound. Memory bound means execution units getting starved because of the congested memory. Core bound means execution ports utilization is suboptimal. Our first effort to mitigate the backend bound is to prohibit the memory bound by developing the VRAN system on an alternative B-phase server. The B-phase platform we use is W2195, which has higher cache size. The table compares the cache size of the YP server and the B-phase server. The figure shows the memory bound and core bound on the YP server and the B-phase server. Our finding is that although the memory bound is significantly mitigated by the larger cache resources, the core bound overhead becomes worse on the B-phase server. The contrast of the lower memory bound and the higher core bound on B-phase server platform makes the overall backend bound stay almost the same to the YP server platform. Then we use the B-phase server as our basic platform because its cache size is large enough to rule out the memory bound impacts. We look into the OAI platform submodules to find out the root cause of the high backend bound. We find that the reason for the high core bound overhead is caused by the SIMD instructions used in the variant system. The high core bound of the SIMD instructions is due to the limitation of available ports for SIMD instruction. As shown in the figure, the SIMD calculation instructions ALU ports are port 0, 1, 2, while the general scalar ALU ports are port 0, 1, 2, and 3. Consequently, the maximum IPC value involved in the SIMD calculation is 3 compared to the ideal IPC value of the scalar instructions value, which is 4. However, the Intel VTunes does not distinguish the SIMD and scalar instruction. Our profiling reveals that the data enrichment process suffers severe low memory bandwidth utilization between the ports registers and the L1 cache, since it only utilizes the load and store ports in the processor. The original data enrichment process purely utilized the load and store ports of the processor to do the data enrichment. The bandwidth utilization for the original process is 16 bits per cycle. To overcome the bottleneck, we examined the CPU architecture and found that the idle ALU ports can be utilized by the data enrichment process. Accordingly, we propose arithmetic ports consciousness mechanism (APCM) to leverage these idle ALU ports concurrently with the load and store ports to solve the data enrichment efficiency problem. As shown in the figure, after the data is transferred directly into the user space by DPDK, APCM utilizes the ALU ports to batch the data before storing them back to the cache. And this will elevate the backend bound and meanwhile promote the bandwidth utilization between the registers and the cache. The figure illustrates the process inside the processor. This is the benching for S1, and this is the benching for YP1, and this is the benching for YP2. As shown in the figure, 3 instructions can be implemented in one cycle by 3 parallel ports. Completing benching S1, YP1, and YP2 will totally require 17 instructions and 6 cycles. The requirement instructions and cycles will be the same for the SSE 128, AVS 253, and AVS 512 under our APCM mechanism. Based on the procedure of the APCM mechanism, we can calculate that the bandwidth per cycle under APCM will be around 67 bits per cycle, 134 bits per cycle, and 270 bits per cycle for the SSE 128, AVS 256, and the AVS 512. And in this section, we evaluate the performance promotion by our proposed mechanism. First, we evaluate the processing time for UDP and TCP under different packet sizes with original and APCM mechanism. The figure demonstrates that the APCM decreased the processing time for both UDP and TCP packets from 12% to 20%. This section demonstrates the SIMD module processing time. For the registers with the wires 128 bits, 256 bits, and 512 bits, the data enrichment process time proportion decreased from 13%, 17%, and 19.5% to 4.7% 3.4%, and 1.8%. We then estimate the macro value under original mechanism and APCI. As shown in the figure, we can observe that for racer with the last 128 bits, 5 256 bits, and 512 bits, the return percentage increased from 55%, 52%, and 48% to 97%, 96%, and 95%. The main backend bond store decreased from 44%, 48%, and 52% to 3%, 4%, and 5%. And the IPC source from 1.2, 1.1, and 1.05 to 3.6, 3.5, and 3.3. And that's all my presentation for the paper. Thanks for hearing. Any questions?